Okay, for this second part of finding volumes, we're going to talk about how to find the volume if you know what the cross-sectional area shape is. So let's go back to what we originally know. We know the volume of a solid is the area times the height. So the area of the cross-section times the height, that's how we've broken things down. So if I could take this and I know the area of this, we multiply it by its height. We'll call the height in this direction. These will be my delta x's, say. And I could find the whole volume of it. So it's the same concept. The only thing different is that we're not revolving about an axis on these. We're not rotating them around. We know what the cross-section will look like, and based on what it looks like, we're going to find the volume. So the formula doesn't change in this aspect, is that the volume is the integral of the area times your dx's. So again, your widths times all your different slices all the way along the bounds from A to B, that will give you the volume. Again, if we do it in the y direction, perpendicular to the y-axis, that's how I'll make my slices. That hasn't changed. For now, everything is perpendicular to the x-axis. The slices are perpendicular. If we're doing it in the y, they're perpendicular to the y-axis. So the slices will be this way, so it'll be like moving up from C to D, summing up all those slices. So that hasn't changed. But again, what has changed is instead of revolving about an axis, revolving about a line, I know what that cross-sectional shape is going to be. So for this first example, these are how these problems will be presented. Find the volume of a solid whose base is bounded by the lines f of x equals 1 minus 1/2 x and g of x equals negative 1 plus 1/2 x and x equals 0. The cross sections perpendicular to the x-axis are equilateral triangles. Okay, so the cross sections, first of all, let's take a look at what my two equations are. I've got 1 minus 1/2 x. So up here at 1, and then this is this line right there. Then I've got my other line. The other one is negative 1 plus 1/2 x. So here's at negative 1. Here's my second line. Now, here's where you have to kind of get a little imaginative. If I could tilt this, I would, but the software won't let me. So here's what's happening though. I should have maybe used a couple different curves to show you, but that's okay, instead of straight lines. But here we go. On this, I've got cross sections perpendicular to the x-axis. Let's do this in a different color. Cross sections perpendicular to the x-axis are equilateral triangles. So these cross sections perpendicular to x are equilateral triangles. So imagine this coming out of the screen at you. That's what's happening in here. I've got equilateral triangles right there. So coming out at you. So if software out. Okay, so this right here, let's go ahead and graph it again since it cut it out for some reason. We've got this blue line, and we said that we had this red line. So I don't know why the software had a glitch right now and just cut all this out. But then we have these purple triangles coming straight out at you, equilateral triangles, to make this three-dimensional shape that has a base that's an equilateral triangle, that's these two lines, and these tops that are equilateral triangles. So since it's equilateral, the tops get smaller as you go towards this front part, this point. So they start off tall and they thin down to a very sharp point at the end here. So that's that three-dimensional shape. Since we know they're equilateral triangles, I know that I can find the area of an equilateral triangle. That's 1/2 times the base times the height. That's the area of a triangle. Now let's get more specific. Since it's equilateral, all these sides, if this is the base, that's going to be B, that's going to be B as well. Well, on an equilateral triangle, I know that this angle is 60 in there. Applying my 60, 30, 90 triangle principles, this piece right here is B over 2. So this will be B, and then this height will be B over 2. B over 2 times the square root of 3. So the area for this triangle, 1/2 times the base times the height, 1/2. Our base is B, and we said our height is this now, the B over 2 root 3. So I'm finding a formula for the area of an equilateral triangle. That's what I'm doing right now in this problem. I get B squared over 4 root 3. One of the common ones on an AP test will be cross-sectionals that are equilateral triangles. Another one will be cross-sectional areas that are squares. Another one, cross-sectional areas that are circles. They try to use, or isosceles triangles, they try to use basic shapes. They don't want to confuse you with something too complex. So those are the ones we're going to focus on, and those are the ones we're going to practice. But for this one, let's finish on. So I have the area of this equilateral triangle. Well, the volume, we said, is equal to the integral of the area. Well, how do I get that area? Well, I need to find what this base length is, right there. I'm given two equations. The distance from the red line to the blue line right there is the length of my base for every single one of those equilateral triangles I've created. So that means I need to take the red curve minus the blue curve. And that's what I've done. Here is the red curve, the top one. Here is the blue curve. And I've subtracted those two, and I get this equation, this final equation, 2 minus x. That is the length of the base. So we go back to our volume formula. The volume is the integral of the area along all those slices. So in this case, it's going to be from 0 to 2, y2 over here, because that's where the point of intersection is at 2. And we're going to start from 0. So from 0 to 2, and let's substitute this in. Notice there is no pi in this. We're not rotating. We don't have a circle. So there's no pi in the formula. This is just the formula for the equilateral triangle over those bounds. So we plug this in. We know the base length now is 2 minus x. So we're going to say the area is root 3 over 4. Again, this is where I'm getting it from. Times this base length, which we said was 2 minus x squared dx. And I go ahead and integrate this, and I'll get to root 3 over 3. Okay, and I want to thank Mr. Ben May, one of my students, who looked on that interweb and found this picture for me. This is what we're looking at for this particular problem.